Hi again, everybody, and welcome back. We're continuing our chapter on potential energy and conservation of energy, and now we're finally at the point where we're talking about conservation of energy. Now, remember that energy that is conserved or work that is conserved means that everything is accounted for. It's not lost. There's no work or energy lost in any kind of change in the system right there. But it can be converted into a different form. The two different forms of energy that we've talked about are kinetic energy, all right, and potential energy. We talked about how the fact that the work kinetic energy theorem says that the total work that is done, all right, is the result of the change, or results in a change in kinetic energy, all right? And if that work is conservative, like with gravity or with a spring, we're reminded that with conservative work, it results in a negative change in potential energy. So if both of these statements are equal, that is, this total work done is done by a conservative work, or done by conservative forces, then we can combine these two and say that the change in kinetic energy results in a negative change in potential energy, and vice versa. One way to think about this is, let's just I'm going to draw a line right here, okay, and I have a ball that is up here in the air. So this is the ground, all right, and we have a ball some distance up in the air. So it has potential energy. The potential energy initial is, I don't know, 5 joules of potential energy. All right? It has the ability to fall down to ground because gravity is a conservative force pulling it down. We'll say it's got 5 joules of potential energy. But when it's up here in this position, at rest, it's not moving. So the kinetic initial is 0 joules. Well, let's say we let that ball go. All right? We drop it. And I'm going to use a different color right here. We're going to drop it down so that now it's at the ground. All right, and I'll use a different color again. So it's no, I'll just make it red. I don't want the arrow to confuse anything. The ball is down here now. Okay, so it falls through this distance, whatever it is. Okay, our initial kinetic energy was 0 because it was at rest. It was ready to fall, but it hadn't. But it had potential energy because it was raised up some distance, mgh. Now we've allowed it to fall down. And so right before it hits the ground, now we're not talking about after it hits the ground, but right when it hits the ground, it is moving. There's little moving lines right there. Okay, it's just about to contact the ground. So, does it have kinetic energy? Yes, it does, because it's moving. So kinetic energy final equals something. Well, what is that something? Well, let's just hold off on that for a second, and let's ask ourselves what the final potential energy is. Well, it has fallen down from its height. It has no more potential to fall. It has used up all of its potential energy, so the final potential energy is 0 joules, which means if all of that is converted to kinetic energy, it must have a final kinetic energy of 5 joules. So this energy that was previously stored as potential is now exerting itself as kinetic energy down at the bottom here. So it's simply changed from potential energy to kinetic. So we have a negative change in potential energy, that's from here to here, and we have a positive change in kinetic energy from here to here. And that's what our statement about the conservation of energy actually means. The conservation of energy means that between any 2 points, if an object changes its position, the kinetic energy, the initial and final kinetic energy, the difference or sum of those two, is going to be equal to the difference or sum of the potential energy. Now remember, we said that the kinetic energy was a positive change, so we've got final minus initial. And potential energy is a negative change, so it's initial minus final. If we take all the initials and put them all to one side, so the initial, let's say, comes over here, all right, initial potential energy, and the final kinetic energy get put over here, well, that's going to mean, in fact, I should erase this. If we add over the initial potential energy, so it's going to be negative K initial, actually we're going to be subtracting it over, right? Minus U initial equals, and then we take our K final and subtract it so it's over there. It's going to be negative U final minus kinetic final right here. We just get rid of all those minus signs. We have a statement about our initial condition. That is, the initial condition being the sum of the potential energy and kinetic energy, and our final position, the final position where that object has moved to. It's the sum of the final potential energy plus the final kinetic energy right here. So we can really say that this right here is all the energy, you could say all the mechanical energy initial equals all the mechanical energy final. And that's what this means. At any one point, the energy, the mechanical energy at any one point, whether you're talking about potential or kinetic or both, is the sum of those two. So if we've got initial right here, energy initial, so it's going to be potential initial plus kinetic initial. If we're talking about energy final, it's going to be potential final plus kinetic final. So if we have all our energy conserved, if all energy is conserved, that means none of it is lost between two positions. So that means that between the initial position and final position, the two energy states should be equal to each other, as long as we're dealing with a conservative force. That is, a force that does not result in any loss of energy right there. All right? So the way I like to write it is usually like this. I like to say energy initial equals energy final. And again, at any one of those points, energy initial is going to be the sum of potential and kinetic initial. All right? Or energy final is going to be the sum of potential and energy, or potential and kinetic final right there. So as long as we account for all the potential and all the kinetic here, and all the potential and all the kinetic right here, we can solve for any one of the unknown energies of the object within that system. All right? So that's kind of a lot to digest right there. I realize the last couple slides have been talking about energy and sums of energy. It may just be helpful to apply this to an example. And instead of jumping right into that, I'm going to just end this segment right here. The next example, 8.6, is an example where somebody is throwing an object up into the air. And I think we'll apply this and hopefully it'll make a little bit more sense. So that is conservation of energy. And again, we're assuming that no energy is lost. That's what conservation of energy means. Let's finish up this segment, and I'll see you on the next one, and maybe we can make some sense out of this by applying it to an example problem. Thanks for following along. I'll see you on the next one.